Hi, everybody. My name is Jennifer Stiso. I'm a neuroscience graduate student at the University of Pennsylvania, and I'm going to kick this series off. So first of all, I want to thank you all for joining us today for the Innovators in Cognitive Neuroscience speaker series. Before we begin, let us please acknowledge the indigenous lands from which we are calling in today. The land I am calling in from and the surrounding area is marked in name by the peoples from which this land was taken, the Lenni Lenape people. Please take an opportunity to reflect on where you're joining us from today. Through the recognition of past harms, we can resolve to create more equitable and humane futures. So I'm going to go ahead and introduce Dr. Momennejad now. Dr. Momennejad received formal education in software engineering and philosophy of science before going on to pursue a PhD in psychology at the Humboldt University of Berlin. She's built a really fascinating body of research that investigates sort of the theory and practice of how individuals model and interact with their environment using reinforcement learning, behavioral data, neuroimaging, and neural recordings. And she is now continuing this research at Microsoft Research in New York, where she's a senior research scientist. So please join me in welcoming Dr. Ida Momennejad.
Thank you so much for that wonderful introduction. And thank you for also acknowledging the indigenous lands that we all occupy these days. I've been told to start by sharing a cause that I'm passionate about. So I thought that probably everyone is going to talk about something related to politics. And given this is Dartmouth, probably about women's safety and about gender disparity. But what I would like to highlight is there are a lot of homeless people, and in New York City, a cause that I am passionate about supporting is Women and Children's Shelter that provides safe housing and critical services to help women and children who have become homeless either due to family violence or due to poverty or due to COVID-related issues. It's been going on for more than 30 years, and they provide a lot of healthcare and also schooling for children. And I think that it's for all of us who have never experienced what these sort of women and children might have experienced, it's important to remember them too. Sometimes we get so lost in our kinds of troubles that we forget there's something much more basic going on. So if you'd like to check it out, last year, WIN served 9,200 people, so you could consider this as a place to donate. Okay, I'm going to tell you a little bit about some of the work I've done. I want to keep this interactive, so if you want to ask questions, please do, but please only ask clarification questions in the middle, and we can leave the discussion at the end. I have exactly a little less than an hour, so I'm going to monitor the time and maybe skip over some things if people are interested in other parts. I'll mostly focus on what I've already done, then, so some of you might have seen before, but towards the end, I will definitely reserve something like 10 minutes to show you some new stuff that I'm doing. Not in detail, potentially a little bit of bits and pieces, but hopefully you will get a glimpse into where I'm going. I spent a lot of time thinking about what algorithms our brains use when they face certain kinds of very complex but natural everyday problems. One of such problems is long distance navigation. So for instance, when I'm trying to plan to go from New York City to Tehran, there are some considerations to take at different scales of abstraction. At a higher scale, I might think about how much time it might take to just take a plane from New York City to Tehran, or how to get there. On a lower level, mid-level, I might think about, oh, how do I get from my home to the airport and from airport to my dad's home? On lower levels, I might think about visas and what I can take with me and a lot of other things, and might realize that I might need months of preparation to ensure I can come back or things like that. So it's not just in these kinds of navigation related issues, but also in social problems such as social inference, as you can see here, games, and also problems as simple as cooking or playing music that I do every day, that we need these kinds of multi-scale representations or moving between these multiple scales in order to make the right decisions or realize planned action. So there is a way in which brain's learning algorithms are very tied to memory and planning. remembering what the path is, planning what to do next, what are the right steps to do it. Now, the approach that I take to study this, what are the algorithms that the brains use for learning, memory, and planning? The approach that I use is one in which I consider a number of algorithms, then I formalize them, then I create behavioral tasks that these different algorithms would perform differently on. That gives me the opportunity to have humans perform these tasks and then compare the performance of these algorithms on the task with the performance of humans. So the first step is to compare the behavior on the same task between humans and the different algorithms that are the candidates for how the brain might be solving these problems or the task. On a second step, now we can look under the hood of the winning algorithms and see what kind of representations did they learn, and then use either fMRI or electrophysiology to look inside human brains and see whether those representations that we find in humans, in my case, and some people use other animals, whether those representations in brains correspond to the kinds of representations we expect to get from the agents or the algorithms that we tested. So this two-step is something that you would see. And I'll show you later on that in new work that I'm doing, I'm using these steps in order to create human-like navigation in AI. But we'll get to that. So the approach that I'm using is reinforcement learning. In a very simple sense, this is an approach where there's an agent, it takes actions, sometimes learns representations, not all kinds, and then plans to achieve goals. It's not really plausible for the past 25 years, there have been research at the intersection of the brain, cognitive science, and reinforcement learning. It enables abstraction, hierarchy, generalization, and transfer. It enables a formalized mathematical way of looking at these things and a way to test behavior of agents and humans on the same tasks. Why would I use reinforcement learning? This is an approach that it allows us to simplify the world and simplify tasks and problems with very specific constraints that are mathematically modelable and tractable. For instance, the way that you would hear about the RL problem is that it's one where given a task or a goal in an environment, there's an agent that learns a sequence of actions or a policy to maximize expected value. This expected value is often minimally described as a discounted cumulative reward over future states. Now, there are other variations to this. One variation is when you have intrinsic rewards as opposed to just extrinsic reward. Another one is one in which it's sparse rewards or no rewards, and you just need to learn the structure of the world. So the most simple case is this, but there are very many variations on it. One interesting aspect of reinforcement learning is that it simplifies the world into states. For instance, in a grid world setting, as you see here, each of these squares are a state. And there are actions. For instance, in this case, it's left, right, up, and left, up and down. And there are policies, which is a sequence of action. For instance, this green path that you see here is a policy. This dashed line that you see here is a policy. And there are optimal policies. These are policies or sequence of actions that maximize reward. So this green one is an optimal policy, for instance. And note that there can be multiple optimal policies. It's not just one in any given environment. And then there are options or abstracted policies. Because it's possible to have multiple policies that achieve the same start to end move, it's possible to abstract it as this. So for instance, as you can see on this right image, going from the top left corner to the top right corner in another room and passing through this door, there are many different ways that you can do this with your movements on the grids, but in an abstract sense, it would look something like this. So that's an abstraction of the, and then you have options, which are abstracted policies, and you have eigen options, and so on and so forth. This allows us to have a very simple framework with which to capture simple things like states and actions, as well as more complex things like policies and eigen options that are the linear combination of which can give us any other option. So that's the special thing about eigenoptions. They decompose options into sort of parts that you can later on combine to produce any new options. So those are very interesting as well, especially for sparse reward exploration and structure learning. Okay, so let's go back to the question of what algorithms brains use. These brains of ours have evolved over millions of years to enable flexibility, and that flexibility is quite important. Two very simple ways where we can define this behavioral flexibility in the context that we've been discussing is we need to be flexible when reward structures change. So in the case of my flight, my flight gate might change, or the coffee cart in the airport might move, which means I might completely lose my flight. So it's important for me to flexibly find coffee. Another thing is that the transition structures might change. For instance, the subway lines in New York City, sometimes A and F run on each other's lines, 2 and 1 run on each other's lines. It's important for me to pay attention to those cues as I'm going through my path, and these may change partially, and so I need to integrate them very fast, flexibly manage to get to the airport on time. Or they can be escalator construction at the airport. The approach that I have engaged with throughout my work is one where perspective memory and predictive representations are represented along posterior to anterior hippocampal and posterior to anterior prefrontal hierarchies in the human brain. And you can see here a series of papers, some of which I will discuss today, and perhaps this review paper on the top might be a good place to take a look at a short, brief overview of all of them. Now, let me try to explain a little bit what all of this that you see on screen means in the next half hour or so. So the idea of cognitive maps, as many of you know, is not a new concept. There's a review paper in 1948 by Tolman that summarizes work done by himself and by many others over the 20 years preceding this paper. One of the most interesting studies that is discussed here is that of the paradigm of latent learning. This is interesting because it goes against the behaviorist dogma of the time that says animals can only learn something if you're reinforcing them directly, if you're rewarding them. In the case of this experiment, Tolman compared animals who entered the maze and had already some reward there with animals who had navigated the maze without any reward being in the maze, and then on a 3rd day or on a 7th day introduce a reward there. What he wanted to see or show was that the animals that had navigated the maze before were faster at finding the optimal trajectory or the optimal policy to the location of rewards when they were introduced. What does this mean? It means the animals who had navigated the maze without any rewards had been learning something. They have been learning the map. And later, when reward was introduced, they could use this map to learn it faster than animals who entered the maze without any experience of the maze and navigated to find the optimal policy. This was revolutionary at the time, believe it or not. Later on, in 1978, there was this book that sort of furthered this understanding. And there was, since the 70s until the 2000s, there were the Nobel Prize winning discovery of hippocampal place cells and entorhinal grid cells, and also indication of prefrontal cortical cells and ensembles of cells in basically map building and map-based navigation. The interesting thing here, I personally don't study place cells and grid cells, but the interesting and important key thing here is that any account of an algorithm that's learning representations that can be useful for navigation will need to be able to explain these findings and other findings about place cells and grid cells. For instance, the fact that they get skewed towards the direction of the goal. All of these need to be explained by a computational account that's trying to explain how the brain learns representations of the world and uses them for planning. So I hope that we get to that, and please feel free to ask me questions about this. Now, one thing that was not pertinent to the works earlier on was, what do these cognitive maps actually look like? Okay, we have cells, we have grid fields, but what is the structure by which the brain maps something in the world, a series of choices, decision trees in the world, in its representations? One possibility is that the brain builds one-step associations, and one-step associations only, that it learns in the environment, and at the moment of decision unrolls or unfolds these associations to compare different trajectories of possible policies and choose the one that maximizes reward. That's one option. This is in fact what model-based RL says, as we will see in a bit. Another option is to think about this kind of a semi-flexible but more efficient approach that has already figured out that there are these jumps or multi-step possibilities of reaching from some points to others. And then at the moment of decision, would use this in a flexible way to find its optimal trajectory. So first, let me tell you a little bit about that second approach and compare it with the model-based approach, the successor representation learning and replay, which is something that I've proposed. And I'll contrast it first with some more well-known reinforcement learning approaches in cognitive science and neuroscience. So in order to make things easier, let us assume that the world is very simple. Let's say that the world has 6 states, and it's from location 1, you transition to 3 with probability 1, and 3 to 5 with probability 1, and then you get $10. From location 2, you transition to 4 to 6, and then you get $1. If I right now asked you if you prefer 1 or 2, if you were an agent that preferred paths that give you more money, you would choose 1. Now, what happens if I, for instance, tell you that I put another amount of money in 5 or 6 that are different, and then you didn't have the time to go from 1 and see that it's reaching to a different value, or from 2, and you had to decide whether you need to change your decision at location 1 or 2. How would your brain handle that? So just to give you an idea of what these experiments look like, let me just show you this. So here we are in that state 1, for instance. The second room is like that state 3. Notice that the colors, context, and music is helping the person who's watching this to know that there are different states. And then you get your money there. So let's see how a model-free reinforcement learning approach just learns the value of things. So a model-free approach is one in which there is a state, you take an action, you see a reward. For instance, I go to Brooklyn Library, I write and I feel rewarded. Then I can compute the value of state S. I'm taking action A at state S as the old value that I knew about it, plus some kind of a learning rate between 0 and 1, because you don't want to immediately update everything with every new information. You want to give some time to acquire that information, to see it over and over and see if it's going to be consistent or not, and some reward. For instance, the value of going to the library, state being library, and action being write, is the old value of it. Let's say the first time I had 0 because I didn't know. And then I all of a sudden figure out it's a lot of reward. And let's say I have a learning rate of 0.5. So I will update this value. But it's not just the reward, right? Because the second time that I arrive, I have already some reward in my value, but because of the alpha, it's not the entire reward. So how do I handle it? So let's just generalize this example that I mentioned into a simple but very effective way of learning, a learning approach that's called temporal difference learning. The value of a state in action is the old value of that state in action plus a learning rate times a prediction error. And the prediction error is how different is this from what I expected? What does that mean? It's the reward I observed minus the old value that I thought I was going to get here, plus the discounted expected value of the new state that I observed. What does that mean? Let's say that I go to the library and then I write and I get some reward. And then afterwards I pick up a book. This is S prime over here. And then I take another action, A prime, for instance, read, and then I get another reward. So there is a value to this S prime, and I have saved that somewhere. And there is a value to this S, and I have saved that somewhere. this time that I arrive to the library and I write and then I pick up the book, I can update the value of writing. I can update the value of S and A by seeing how much the discounted value of the next state would change it. So what is that? Why discounted? Because this is not something I'm receiving the reward for right now. Some value between 0 and 1 can discount because I'm going to get this in the future. So prediction error, in short, instead of just the reward, I can use prediction error, which is the reward I observe plus the discounted expected value of the next state that I'm observing, that I've arrived at, minus the old value I expected of S. So if I've done this very often, this prediction error would be 0 because I have incorporated all of this into the SNA. So the prediction error would be 0 if I go and do something consistently and everything is the same. This TD prediction error obviously has shown up a lot in neuroscience. You can take a look at this 1996 paper. It has been associated with dopamine function, but now there are some more complicated stories about it. This is not the focus of what I'm going to talk about. This approach, this model-free reinforcement learning, does not learn any map of the world. It learns a table of the value of states and actions, that's all. And that means that it doesn't quite know what states it's going to see. It can't just simulate in its head what states it's going to end up with. It doesn't have that information. It just can update its value. When it arrives at S prime and it sees S prime, then it can look up the value of S prime and update value of S, but it cannot quite see the state itself. So although over time, this gradually has this expected value of future states, it has no idea about the map of the world, which means it's fast, but it's not flexible. If you partially change things, it has already cached the value of things on the basis of old map of the world. So it doesn't transfer if rewards or maps partially change. It can't figure things out. Another hypothesis is model-based reinforcement learning that separately learns a map of the world, which is the probability of transitioning from state S given taking action A and ending in state S prime. So probability of ending up in state S prime given you started in state S and took action A. And the reward associated with state S and taking action A. Note this is not the value, this is reward. To compute the value, you combine these two. So if I turned this map into a matrix, this is what you would see. On the X, you would see the state where you start from, and on the columns, you see the states that you end up in. And then you can see that from 1 to 3, for instance, there is 1, but I don't know if I'm going to end up in 5 or 6 or 4 after that. What I need to do is iterate. So I go from 1 to 3, I go to row 3, and I see that that leads to 5. And now I can know, for instance, that the value of 1 might have something to do with the value of 5. It's very flexible, but it's very slow because of this. So to give you an idea, this is V star. Every time you see star, it's the optimal value. So it's the best you can get. And this is max A. This is the actions that are going to maximize the rewards. And this is an iteration, as you can see. For the sum of S primes that can be observed, you look at the probability of ending up in that state. And remember this action of all the actions are the actions that will maximize value times the discounted optimal value of that next state. So this iterative way is going to make me figure out what the value of 1 is by iterating over values, summing the values of these different sort of states. At the moment of decision, it has to unfold and iterate over all of them to be able to decide. Another approach that I'd like to discuss, and I mentioned a little earlier, is the successor representation, where you don't store, you again store separately. You factorize a map of the world and the reward separately. However, the map is not a one-step probability map. This map is one where you have expected future occupation. On average, how many counts do I expect to visit this again? How often do I expect to visit again? State 3, for instance, if I start at state 1. And here you multiply the probability of transitions with some discount parameter and also over multiple steps, as you can see here. For instance, you can have expected future occupancy of 1 to 5 is computed like this. It's this gamma squared because there is 2 rounds. Basically, you multiply this gamma times probability of transitioning from 1 to 3 by the second one, and you get gamma squared probability of 1 to 3, probability of 3 to 5. This can be learned very nicely via TD learning, as you can see below, right here below. I just want to not move my pointer because it brings this kind of thing. Okay, so as you can see here, M of S, which is the multi-step map, the successor representation of S, equals the old successor representation of S plus learning rate times some prediction error. So we've seen this before. But in this case, instead of a reward prediction error or value prediction error, we have a successor prediction error, which is computed as 1 hot S prime. What does that mean? I'm adding a count of 1 and 0 for everything else, just 1 for S prime, because I was in S and I arrived and I saw S prime. So 1 count to that, plus discounted successors of S prime. What does that mean? When I'm in S and I arrive at S prime, I inherit the successors of S prime as well in a discounted way. And that's important. I'm inheriting its future. Minus the successor representation of S. Because if I've been to S prime often, this is already incorporated in M. And so this prediction error would be 0 if I've done it a lot. But if I haven't done it before, I will have a prediction error and I will update my successor representation. And this is a row. This M is not one singular scalar value. It's a row, right? So, or if you're doing, because you have the row of S, sorry, firefighters passing by. You have a row of S, and then in that row, you are adding what you're seeing now. You're adding state S prime, and you're adding a discounted successors of S prime. This very simple approach via temporal difference learning, it can learn the successor map for us in absence of rewards separately. And then it can learn, rewards are learned separately, which I'm not showing here. And then I can combine them in a very cheap way, linear combination at the moment of decision. Combine this M or the multi-step map, which as you can see depends on some gamma and also on some pi. And that pi is our policy, the particular sequence of things that I have experienced to get there. And it's much simpler, it's much cheaper to compute and faster to compute than the model-based one. So to put them side by side, on the left, you see model-based reinforcement learning approaches where you have the probability transitions and the rewards separately. On the right, you see multi-step map factorized separately from the rewards. And if you can just look at the rows, you already see what I'm talking about. In one, we needed to iterate to figure out whether 5 follows 1. But in the second one, if we are at row 1, we can already see that 1 leads to 3 and 1 leads to 5. We don't need to iterate in order to find that out. So this is a nice thing that you can get. Now, let's see how we can test which of these models. As if you recall, the first step was figure out what are the algorithms you think might be underlying, in this case, the cognitive maps, right? So let's now test it. Let's have this example that we just gave tested to see which one of them is underlying behavior in humans. Here's a task that makes it possible. Remember that we had 2 forms of flexibility minimally that we talked about earlier. Rewards might change. So let's say during learning, you learn very well this example that I had mentioned before. During relearning, you no longer see 1 or 2. So you see partially other things in the world. You see that 3 now leads to 5 as before, but it leads to $1 this time. So the reward has changed. And 4 now leads to 6. So the rewards there has changed as well. I haven't seen directly going from 1 and giving $1 and going from room 2 or state 2 and getting $10. So how does my brain update this? Another one is transition revaluation, where the rewards didn't change, but when you were in state 3, before you were in state 3, it led to 5, but now it leads to 6, and 4 now leads to 5. So in our experiment that you saw before, for instance, sometimes you open a room's door and it opens up to a different room than what you expected. How about this one? So usually, so let's go ahead and test it. Before that, let me just ask if anybody can unmute themselves. Which one of these 2 can model-based solve? Any guesses? Which one of these 2, reward evaluation or transition evaluation, can model-based reinforcement learning solve? Any guesses are good.
We had somebody post in the Q&A, Jane Hahn said transition reevaluation.
I see. So I see that people say that they can't unmute themselves. I'm sorry to hear that. You can post in the messages in the chat. I can see the chat, but I can't see Q&A. So model-based reinforcement learning can solve both of them. And it takes equally long amounts of time to solve them. Which one of them can model-free solve? Can somebody write in the chat? I'll take the first answer. Reward. Model-free cannot, thank you, Linda, model-free cannot solve any of them. So model-free cannot solve any of them. Why? We will see in a minute. Which one of them do you think successor representation can solve? I'll take the first answer in the chat again. Transition. The other way around. Successor representation without replay can only solve reward. It can't solve transition. So let's take a look at what I mean by everything. And thank you so much for your participation, everyone. This shows me that you're not asleep. So as you can see here, this is, let's look at the case above. This is the reward evaluation. This is the model-free learner. Model-free learner has learned that 10 is associated with value, state 1 is associated with a value of $10. Let's say that the discount factor and the learning rate are both 1, just to make it easier. And it has learned that 2 is associated with $1. When things changed partially in the world, it learned that 3 now leads to 1 and 4 leads to 10, but it didn't get the chance to update 1 or 2. So model free is still going to think that 1 gives $10. So it's going to fail at the reward evaluation. Successor representation, however, it knows the map of the world very well. And the only thing that has changed is the reward associated with 5 and the reward associated with 6. And because it learns rewards and maps separately, it has updated the reward. So it can correctly infer that the value of 2 is higher now and correctly choose 2. Model-based learning says 1 leads to 3, 3 leads to 5, 5 gives $1, 2 leads to 4, 4 leads to 6, 6 gives $10. So it iterates over all of the map, and then it can say correctly that it's 2. So it takes more time than SR, but they both give the correct answer. Now let's move to transition evaluation, where the rewards don't change, but the transition structure has changed. Model free as before. It does not update 1 and 2 unless it goes into 1 and 2. So it's not going to be able to do it. SR, on the other hand, it has grandfathered this old map because it hasn't revisited 1 and 2 to figure out that the map of the world has changed for 1 and 2. So because rewards haven't changed, but the map of the world has changed, SR alone that hasn't been revisiting 1 and 2, either via actual experience or via replay, is not going to be able to solve it. It's still going to think it's 1. But model-based, as mentioned before, it's again going to do all of the computation. 1 leads to 3, 3 leads to 6, etc. So it's going to go over all of them and figure out that 2 is the correct answer. So just to put all of what we said, all of the predictions in one slide, here on the y-axis, you see revaluation score. 0 means they didn't change their behavior from before, and 1 means they did change their behavior from before. Model free can't do any of those 2 things. Remember, this is retrospective evaluation, so it's important. It's a retrospective evaluation when they see partially the world. They don't see 1 or 2 to update them. So they have to use some kind of either replay or forward model to use it, to update it. So model-based here can do both of them equally well. A combination of model-free and model-based, whether it's DINA or whether it's just a combination, is going to be able to do both, again, symmetrically. SR alone, without replay, can only do reward evaluation, but it cannot do transition evaluation. However, SR DINA, which is what I proposed, which combines successor representations and replay, can solve both of them, but asymmetrically, because it's going to be better at reward evaluation, but it's not going to be as good at transition evaluation because it's going to need more time to use replay to update its map. What does that look like? Oh, first of all, after half an hour, we see some human data. Here you can see human behavior. Y-axis is our evaluation score. 0 means no change, and 1 would be maximal change. As you can see, humans are better at reward evaluation compared to transition evaluation, which fits with this prediction of SR dyno. Let's take a closer look. We had a control condition where things didn't change. Why was this important? Because we don't know, maybe people just forgot what was the good choice in the beginning, and all of the behavior that we see that has changes because they don't remember. This control condition shows us that they weren't forgetting. So if we don't change anything in the world, they know that they have to stick with what they were doing before. But as you can see in reward evaluation, they are updating, they're changing their behavior more than in transition evaluation. Someone might say, hey, this could be a speed and accuracy trade-off. Maybe they were just slower during reward evaluation. So let's take a look at reaction times in the second plot on the y-axis in seconds. And on the x-axis, you again see the three conditions that we had. As you can see, in fact, they were slowest at transition evaluation. They took more time. So this is not a speed accuracy trade-off. In fact, the accuracy of performance on transition evaluation was correlated with how long they took with their response times. So what does this tell us? This together tells us that this model, the SR dyna, that combines replay with the successor representation is likely involved, or at least among these 5 models that we have been considering, this is the model that seems to be most aligned, or the only model that's aligned with human behavior. I did a couple of studies later on using offline replay, for instance, using FMRI to study whether, in fact, I can see evidence that FMRI evidence for offline replay predicts this revaluation behavior. I'm not going to go into details in this because I want to get to other work, but long story short, in the control condition, you have replay here on the x-axis, and on the y-axis, you have revaluation behavior. There was no correlation in the control condition where things didn't change, but in retrospective evaluation of rewards, there was a correlation between replay during rest periods on the x-axis and revaluation score later on during the test period on the y-axis. I recommend that you take a look at this paper of ours from 2018. Another thing that we looked into that you might be interested in is that we had this hypothesis with FMRI that in transition evaluation, the pattern similarity between room 1 and 2 or room 1 and 6 is going to predict how much people are going to make an error. Because remember, in transition evaluation, SR was grandfathering the old relationship between 1 and 5 that was no longer valid. So we indeed did that. We ran a representational similarity analysis, for instance, between state 1 and 5 and 1 and 6, and found that when state 1, we were here, and 1 still looked more like 5, the neural representations in fMRI data when the subject was in state 1 during the test looked more like 5 than 6 in these regions, then subjects are more likely to show error in behavior. So this is telling us when the cognitive maps hadn't been updated the way we expected them to be updated, people showed errors that are consistent with that not updated cognitive map, not up-to-date cognitive map. Anterior hippocampus, orbitofrontal cortex, anterior prefrontal cortex were the regions that we uncovered. And these are regions I was very happy to see, especially this one, because these were regions, as you can see in my earlier PhD work, I had identified in multivariate analysis of fMRI data, that these were regions where the brain seemed to represent future tasks when we were doing another task right now, a capacity known as prospective memory. So we had uncovered a similar region together with other regions involved in the representation of the next step that I'm expecting to come that is multiple steps away. And the extent to which these regions still showed similarity to that state that is no longer up to date, I would show errors that are consistent with that previous relationship that existed between 1 and 5. Okay, I want to say something else about the successor representation that's very exciting. Intuitively, I think this would help you understand why this approach is very helpful. The rows of the successor representation, if we imagined it like a matrix, the rows of the successor representation correspond to what comes next, correspond to the successors, not just in time, but in, let's say, if you have a family tree, if you have a network of associations, if you have a statistical association between certain things, if you have a causal chain, it's associated with successors, what comes next. And the columns are associated with predecessors, or how did we get here? So the column 5, there is going to be a higher than 0 number for any other state that's going to lead to state 5. This is very similar to some concept that we are all very excited about in neuroscience, which is place fields. So my very good friend and excellent scientist, Kim Stackenfeld, has shown that the columns of the successor representation can be used to simulate place fields. And that's a pretty fantastic thing, because as you recall, I mentioned earlier, any good computational account of cognitive maps needs to be able to explain place fields and grid fields, and the zoo of cells, as Tim Behrens calls it in a review. And in another work with Mark Howard, we also showed, another important thing, the eigenvectors of the successor representation correspond to grid cells or grid fields, which is also non-trivial and pretty fantastic that this worked out. And then what we showed with Mark Howard was that if you have multi-scale successor representation, the derivative of it, which is the equivalent of the inverse Laplace transform for the aficionados, it can capture distance to goal. And when we found it out mathematically, we were a little confused how to test it. And we were very fortunate. A few months after that, we saw Sorel's paper where they found a distance to goal cells in the hippocampus of bats. And then later on, a couple of other papers came out, including Salman Qasim's work in distance to goal cells in human entorhinal cortex. Another thing that I want to mention about successor representation is the policy dependence. Remember that pi of m. If this is a rodent in a maze, and this is where the money is, because apparently this rodent is very into money, in panel B, you see the representation of just the location where the rodent is right now. In panel C, you see the successor representation. Which other locations would be highly activated in the representation when the rodent is in this state, given some gamma, some radius, some horizon? If the policy that the rodent had taken was random, it was going in all directions equally likely. If either reward were spread out in the same way or there was no reward, if the policy was the same, the rodent would know that all of these are, places it can occupy equally often. But if the rodent was very intent, either via replay or via actual experience, to get into this money location, and just this optimal policy was being replayed over and over and over again to update one's cognitive map, this is what the map would look like. When the rodent is here, it would basically only see the successors that lead to goal. This is the extreme case of policy-dependent successor representation. Of course, this extreme case doesn't happen as often, but as you can imagine, this would predict the skewedness of the place fields towards the location of the goal, which is something that's observed in rodents. And I recommend that people who are on this call who are interested in this ask me at the end, because I have more to say about this. Okay, I need to hurry up. I just realized it's 12:45. Okay, so we tested this hypothesis also in patients who had electrodes inside their hippocampus because they were epileptic surgery patients. And we were very fortunate that they allowed us they gave us their time to give them laptops that they could observe games such as the one that I showed you earlier on. And then we could collect data using Benke-Fried electrodes. As you can see here, that were inserted into the brain laterally into the hippocampus. So what they saw again was those rooms. Remember, again, it's the same kind of paradigm: room 1, room 2, room 3. When there's reward evaluation, the money at the end changes. When there's transition evaluation, this room 3's door, for instance, opens to room 6 instead of 5, and 4 opens to 5 as opposed to 6. You already seen this, so I can skip this. You already saw this in the earlier space. And then we ask them which room will give you greater reward, and they can slide this to figure out which one of the two they prefer. So one thing that I did was take the cells, and 14 cells in a human is a very good day. Take the cells, firing rates in different rooms, form a vector, and then compare the multi-cell vector of firing for these cells from room 1 to room 2 to room 3 to room 6, and put each of those dot products or correlations into this matrix to form this room similarity matrix, basically, that will give me what kind of rooms look like what other kinds of rooms. If the successor similarity hypothesis is correct, after the transition revaluation for correct induction that 2 is now the right decision, what would we need? What we would need is that room 1 to 3, for instance, could increase, 1 to 4 could decrease. This part is like given from what we had before. But this is the part where we would be excited about. The multi-step dependencies between 1 and 5 and 1 and 6 should change. 1 to 5 should go down. 1 to 6 should go up in similarity. 2 to 5 should go up. 2 to 6 should go down. So this is the hypothesis of hypothesis matrix for changes of room-to-room similarity. And then if we compare this hypothesis, if we compare the measured computed matrix for similarity of neural vectors across these different states or rooms before and after evaluation, then subtracting them should give us that increase or decrease that we observe in the data, so we can compare it to what we expected from our hypothesis. So here's what we see. On the y-axis, you can see changes in multivariate similarity between rooms. On the x-axis, you see, for instance, here you see room 1 to 3 changes, room 1 to 4 changes. As you can see, room 1 to 3 increases in similarity and room 1 to 4 decreases. We expected this. Room 1 never leads to 4 and room 1 always leads to 3, but it increased in spite of the fact that they hadn't seen 1 to 3 transition in a while. And this is the money shot here. Room 1 to 5 similarity has now decreased in spite of the fact that they didn't experience the fact that 1 no longer leads to 5. They have simply pieced things together. And room 1 to 6 increased because now room 1 in 2 steps leads to 6. So we observed changes in this multi-step similarity. This is just data from one patient due to COVID. We are currently waiting to see when we can collect more data, but this was very exciting. Finally, I want to show you one more study where we can then ask, okay, what is the prediction for this multi-scale representation in the brain when we were navigating the world in a realistic way? So do multi-scale predictive maps scale to hierarchical planning at city distances? So I had the opportunity to analyze data from the Moscovich lab, where they had people lie in the scanner and navigate in a virtual Toronto where they live, in one case with a goal, so they knew where they were going, and in controlled for distance conditions, they didn't know where they were going, and an arrow, as you can see here in the image, would tell them which direction to go. So they could see up to a certain horizon, but they didn't know exactly when the arrow is going to tell them to turn, so they didn't know what the final destination was. This is where we tested this multi-scale hypothesis. Our idea was that where you are, if you know where you're going, you should see similarities in the brain towards this further horizon, towards this horizon that's far away from you. And in the other case, you should see towards this kind of more near horizons. And the idea is that these multi-scale representations of states would be represented along the long axis of the hippocampus and then the posterior anterior axis of the prefrontal cortex. We expected the anterior prefrontal cortex to have the highest level of predictive horizon into the future. So the way that we analyzed it, here on the y-axis, you see predictive horizon in meters, and on the x-axis, you see the different gammas or scales of discounting. And what you see here is the map that they were navigating, for instance. So whether it's in the control condition, GPS condition, or the goal-directed condition, you can take either a searchlight in the PFC, as we did there, or the chunking that we did for our regions of interest in the hippocampus. You can see the similarity of those voxels to voxels that are further away along the path for different horizons. Long story short, what we observed was that there was a gradient of this representational similarity for the goal-directed condition. This gradient went up to 1 kilometer almost. But for the GPS condition, it didn't go any further than about 150 meters or 125 meters. And the reason for that is that, well, in the GPS conditions, sometimes they saw some within some horizon of 100, 200 meters, but they couldn't see up to a kilometer and they didn't know where they were going. But in the goal-directed condition, although they weren't seeing where something in that was 1 kilometer away, they were hoping or planning to go there. So they had that representation, that successor active. And you see the same pattern in orbitofrontal cortex. We had similar patterns in the hippocampus, but the maximum we saw in the hippocampus was in fact 0.6 in anterior hippocampus, and in posterior it was 0.1. So it didn't go as far. Okay, so I showed you successor representations, and replay can help form multi-scale predictive cognitive maps that capture human data in human behavior and in human FMRI and in human neurons. And in fact, this perspective might scale to predictive representations in FMRI. And there are a number of studies in context and episodic memory, in optimal sub-goal setting, place cell grid fields, statistical learning, that have shown that the successor representation might actually have something to do at some level of abstraction, not at the implementation level, about the general principle for memory organization. Now I'd like to show you a little bit about some other stuff that I've been doing. And because we don't have a lot of time, I just want to acknowledge my current collaborators with whom I work on memory models, for instance, with John Langford, with the navigation Turing test in games with Katja Hoffman. I am also working on multi-agent models with Serbi, Goal, and evolving value with Serbi, and also together with Rob Shapire. I'm working with Harm Fasayan on a combination of NLP and RL. I also want to acknowledge Neil Lewis Jr. and Aju Adukar, with whom I'm working on ally experiments and theories on how to be an ally. They are both social psychologists. And together with Daniel Belgrave, we are working on data from depression and anxiety from Silver Cloud that uses cognitive behavioral therapy. We have data from 500,000 humans, and we're trying to figure out reinforcement learning ways to find the optimal sort of ways to solve it. Now, before ending, I want to show you one more thing, and I'm again going to ask for audience participation with this. So I would like to ask you to tell me, which of these players do you think is human? I'm going to play video A, and then I'm going to play video B. So please tell me, which of them do you think is human? This is in the project that we have for the navigation Turing test. So I'm going to play video A now. This is the agent that we need to pay attention to. Is this human or machine? And think about why and how difficult this is to yourself. I would love to, well, I would love it if people can, in the Q&A, unmute themselves so I can ask them why. And this is video B. Tell me if this is human or machine. I see that Vasiki already, hi Vasiki. She already says she thinks this is, the video A was a machine. Video B. So we built reinforcement learning algorithms who can play this 4x4 game as well. This game is called Bleeding Edge. It was built by Ninja Theory that was recently purchased by Microsoft. Okay, so I guess Vasiki gave an answer. Video A is human. Another person is A is machine, B is human. So we have 2 counts of A is machine. You are right, A is machine. And I can see that now we are equal. So there is, we are basically, I have another person called R also who says B is machine. So as you can see, it's not so easy. This is the agent that's written by our team. On the A was written by our team, it's RL agent. So I'm gonna do maybe one more. And then this is B. So which one was human or machine this time? Yes, correct. Yeah, so this one was a little easier for everyone to see that A was human because it was more goal directed. So what we do is we collect reasons for this. So first, we built an agent that can play the game. And then we find videos and show people and then ask them, which one do you think is machine and why? The reasons that we find are very interesting because it helps us to optimize the model later on. For instance, they say they were zigzagging in their navigation, or for instance, they get stuck in the walls, or for instance, they go and stand next to an enemy. No human would do that. It's not rational. And it's very interesting to identify these and figure out how we can improve our reinforcement learning models of navigation so that our agents can pass the navigation Turing test so that they can be one day AI sidekicks in games that can play with humans in a more human-like way, for instance. That's one of the areas that I'm excited about. And I just wanted to show you before, oops. So yeah, thank you so much. I am prepared for questions now. And yeah, I look forward to some Q&A in the couple of minutes that we have left.
Okay, that was a really great talk. Thank you so much for taking the time. That was really exciting. Okay, so Neil Burgess has a question in the Q&A, just the first one, so I'm gonna read that one. Hi, Ida, nice talk. Can you tell whether increased neural similarity to the goal state when in the start state reflects the presence of an SR or reflects increased thinking about the goal, e.g. as in model-based path search?
So I'm very glad that you asked that, Neil. Hello, I'm very happy that you're here. So can RL uncover the role of place and grid fields in memory? So we mentioned that perhaps the place fields are the columns and the grid fields are the eigenvectors. And do goals modify the hippocampal and entorhinal maps? And can RL explain this? I put together a couple of studies in the slide. It's almost as if you knew what was my extra slides. On the left, you see studies where place and grid fields actually did shift or form around goals. On the middle, you see where rate remapping happened during trajectories to goals. And on the right, you see situations where there were stable place fields, but there was extra firing at goals. There are, however, other studies. There's inconsistency. Sometimes goals do not modify hippocampal and entorhinal cortex maps, and sometimes they do. And so there's a work that there's a paper that we're writing together with Salma and Qasim directly addressing this. It seems like during non-hippocampal tasks, for instance, when the goal is visible, even though you are seeing it, such as these two examples that I have here, goals do not modify the hippocampal entorhinal maps. Arguably, the agent could be thinking about it if seeing or focusing on it is considered thinking, but it doesn't necessarily shift the sort of place fields. And we think it's when the solution is not hippocampal dependent. But during tasks also that have no policy, the uniform visitation frequency is going to solve it. There's also no use in place fields moving towards any direction. For instance, if there is uniform locations of different goals around, that each of them is going to give rewards. And these are the two papers that we observed where there was no shift towards goals. So we think that first of all, there is a policy efficient representations would lead to goal modulated maps potentially. And I think that it's the same as in model-based path search, that it's when they are just activating that location. This should be very possible to test with timing. So we wouldn't expect if it is model-based, we would expect at least some time for the one-step unfolding of the multi-step trajectory towards the goal. But if it is the case that either an episodic memory strategy is overused in replay and remaps the successor representation, or the successor representation became policy dependent, like that image that I showed you earlier that I can show you again, in those cases, we can expect that it is indeed the SR that moves towards the goal. So I'm just going to show this again. This is a case where if the reward is sort of everywhere, you can see this one. But if the rewards are skewed towards the direction of, if the policy is that rewards are everywhere, or I'm randomly walking around, it looks like this. But if the policy is very much insistent on getting to this location of reward, my representation is going to be skewed towards that direction. This is extreme, of course, there are states in between. And the timing of it should be that it should activate all at once. So when I'm here, you already see the representation of the goal without that extra time that model base would need to unfold the one-step trajectories. So I think that it's an empirical question that people who are fortunate to work with rodents or have, I have been trying to see it in like human data, but to be honest, we don't have enough, and human data is, 14 cells is not great. So if there are people who are interested in collaborating on testing these kinds of things in replay versus sort of simultaneous activation, I think that we can answer that question in an empirical way. But theoretically speaking, this is the reason that it would skew towards goals, and its eigenvectors will also get skewed over time. So it would explain both hippocampal and entorhinal changes. And secondly, behavior that we have observed both in humans and rodents now, the new work that came out of the work by Will Ducote and others, we know that behaviorally, it seems like the one-step model base is not the candidate. So if we put together these emerging bodies of evidence, it seems like model base is not the candidate because of behavior, we already know. And to answer your question, we would need a new sort of control study for it. Thank you so much. It was a great question. Perfect. Yeah, either in MEG or in rodents, it would be great. I can use 1 minute. So I'm seeing that Tor asking, how strongly do you think the kinds of models that best fit human behavior will depend on the specific task? The rooms, people may be able to represent and remember transitions easily, but with different non-place content, maybe they can't, and the model that fits best would be very different. Are there abstract content domains that would best fit by you? Yes. So in fact, I had a slide about this. So if you look at already existing work, what you see here on the left is the context and episodic memory work. So models that explain TC, temporal context model in lists, and how much you're likely to remember something that comes after in a list or before. In memory studies with lists, that's possible to do. There's nothing about navigation or rooms there. And in this other paper, which was by Anna Shapiro, you had different kind of gradients in non-distinguishable kind of like randomly generated shapes that had statistical relationships with one another in large community structure settings. And there was another paper that's not here. It was by Mona Garbutt and Tim Behrens in eLife in 2000, I think 18 or 18 maybe, where they looked at representations inside the hippocampus for navigating a map of object associations. And in that case also, they did not see that. They saw that successor representations was explaining that kind of representation. So we've already seen across them, and we've already seen also place fields for sounds even in rodents, and for others have shown it for social structures or even stretchy birds. So I think there is a lot of converging evidence to know that this is not specific to spatial domains. Do you have a sense how well SR scales for different tasks compared to state-of-the-art algorithms? Do you think brain areas implement SR in different ways? Currently there are a number of other things like successor uncertainties, etc., that have been done by, for instance, Katja Hoffman's group. DeepMind had a paper on theory of mind that used successor representation. So we know that in domains such as social inference, it's also being used and shown to show improvement. Depends which state-of-the-art algorithm you have in mind. And keep in mind that sometimes a state-of-the-art algorithm that doesn't use successor representations explicitly, if you compare the representational similarity of weights in two different conditions, then build that matrix that I'm building, basically doing the same kind of neuroscience I'm doing on neurons, but on the neural networks, you could figure out whether the deep nets actually have a successor representation structure or not. We are doing some work to show that for transformers. Some transformers, sometimes they might be actually picking up SR. And I think that in a lot of other work, one can take a look and see when you actually just slap some layers of DNN on top of one another and see that it solves a task, then we need to do some mathematical analysis of what actually happened in these weights. So somehow like a neural network neuroscience, the neuroscience of neural networks, to or deep nets. This neuroscience of deep nets would allow us to do representational similarity analysis like I showed you in a hypothesis-driven way to see whether some of these state-of-the-art algorithms are actually using that kind of a multi-step representation. Thank you for that question. All right, I have to run to another meeting. In an hour, I'm going to meet people for more Q&A. It was fantastic. And I look forward to meeting you at 3 p.m. again. Thank you.
Yep. Thanks everyone for coming, and thank you, Ida, for giving this talk.
Thank you so much. Mm-hmm.